In this video, we're going to look at different derivative rules. So as a reminder, the derivative is the slope of the tangent line at any given point. Our different rules here, because it represents the slope, if we're taking the derivative of a constant has a slope of 0, so the derivative is always 0. The power rule is the big one, and this is our shortcut so that we don't have to use the big, ugly definition. But if something is written as a power, meaning it has a variable with an exponent, we take our exponent, multiply by whatever number's in the front, and then we always take our exponent and subtract 1 from that exponent. If we have a coefficient, the coefficient just drops down in front of the derivative of the function. If we have a sum or difference, we just take the derivative of each piece and carry down the sum or the difference. That does not work with multiplication and division, and that will be the whole next video, will be about those rules. These you do have to have memorized. I'm also going to ask you at some point to memorize the derivatives of tangent and secant. These are the only two you have to memorize, but all four are very common, so you might as well memorize them both. So sine is cosine, cosine is negative sine, and finally the derivative of e to the x is e to the x, so that's why we like e to the x. So when we're finding derivatives, again, exponents come out front, variable stays the same, and we subtract 1 from our old exponent. The plus just drops. Here, technically, we have an exponent of 1, so if we multiply, we get 2. And this is now going to be x to the 0 power, which is just 1, and 2 times 1 is just 2. Another way to think of this is, remember, the derivative is the slope of the tangent line. Well, this is a linear function. Its slope is always 2. Make sure you label your answer so that we know what this is. So again, to use the power rule, we have to write our terms as powers, meaning they have to have an exponent. So just remember, in a radical function, the exponent turns into a rational exponent. So if there's no exponent, it's a 1, and this is going to turn into x to the 1/3 power. This is still the original. Here, this is going to be 5x to the 1/2 power. And now when we take our derivative, we're going to bring down our coefficient. We're going to subtract 1 from our exponent. And we're going to do the same thing here. So half of 5 is 5/2. And then it's going to be x to the negative 1/2 power. Remember, we're going to label this as our derivative. When we take the derivative of a trig function, we just apply the rules. If we have a coefficient, it drops. The derivative of sine is cosine. And number 2, right now we do not know how to take the derivative of a quotient, so we need to separate this if we can. Because we have a single term in the denominator and it's a constant, I can look at the numerator and take this 1/4 out in front. And all I have to do is take the derivative now of this function. So the derivative, remember, 1/4 drops down. The derivative of cosine is negative sine, but that looks like minus sine. So anytime we have that situation, we'll bring the negative in the front, and we'll bring down our sine. Okay, so this is just some information. Sorry, there should be a derivative there. Remember, our original is our position function, and the velocity is our first derivative. It describes how our position is changing. Position is the level right above it. Acceleration is then our second derivative, and it describes how the velocity, which is, again, this level above it, is changing. So one thing we need to remember is that acceleration is really the first derivative of the velocity, so it can tell me how the velocity is changing. Our derivative describes the change of its original. So remember, speed is how fast you're going. Velocity is both speed plus direction. So if we take the absolute value of velocity, we get speed. You will see this question on the AP test. If speed is increasing, that means velocity and acceleration are working together. So they need to have the same sign. Even if they're both negative, those forces are working together, so my speed is increasing. If they're working against each other, meaning they have different signs, so maybe velocity, maybe my function is going backwards, but the acceleration is pushing on it from the opposite direction. That means my speed will then be decreasing. This is our position function. You've seen this all throughout middle school and high school. Just know that S0 is my initial height. That goes here. Initial velocity goes here. And this is going to be half of whatever acceleration due to gravity is. This you've probably seen in physics. If we're using feet, we use 32 feet per second. Sorry, that's per second squared. Typo. Okay, and then the last example here, we have a diver jumping from a platform. They've given me my function, and they're going to ask me some questions. It says, when does the diver hit the water? So this is asking me to find time. And when we hit the water, my position will be 0. So I really need to solve this function, and I'm going to go ahead and do that for you. Okay, so if we factor and solve, we do see that t equals 2 and negative 1. Obviously, time cannot be negative. That would just be if this function were to continue. That's where it would hit the x-axis. So we're going to say after 2 seconds is when the diver hits the water. The question now wants to know, what is the diver's velocity at impact? So we find velocity by taking the first derivative. So if I take the derivative of s, that's going to give me velocity. And here again, I multiply. Here, the derivative of 16t is just 16. Derivative of a constant is 0. And it wants to know what's the velocity at impact. And impact happened when time was 2. So it just wants to know what's the velocity at time 2. And so here, whoops, sorry, that should have been a 2. So we'll get negative 64 plus 16 or negative 48. Because this is velocity, this is going to be feet per second. We're dealing with feet, we're dealing with seconds. This negative means he's going down, which obviously makes sense.